Good afternoon, students. Let's start with the class. Previous class, I started with the probability chapter. So we had solved some basic problems on probability, and then based on independent events, if any two events are independent, then it is directly P of A into P of B. Today we'll see what is conditional probability. Conditional means one event is dependent on the other one. Okay. Consider event A has already occurred. Okay. So event A has already occurred. Now event B, this is event A. So you can consider this is the first event. Now another event is happening, occurs based on event 1 or event A. Now suppose if you have certain amount of coins, maybe there are some coins in this. Okay. Now you have picked up a coin, different coins are not only this, any other coin, or you can consider maybe some marbles. Okay, different color marbles. Now first one marble you are picking up. One marble you have picked up and kept at the side. Okay, so this has already occurred. So keep at the side. Now this is event 1. Now what you are doing? Now again you are trying to pick up. You are not putting this marble 1 back now. Huh? You are just removing 1 and keeping it aside. Now I'm asking you, what is the second one? Means now again event 2 is what? Picking marble 2. Now what is happening? Second marble what you are picking depends on what was picked up first. Now you have kept it aside. A marble which you wanted must have already come out and gone there somewhere. Okay, so the second event is always already dependent on the first one. So whenever second event is based on the first one, okay, color of marble 2 depends on, may or may not depend also. We'll have to see that. It depends on marble 1 because we don't know what was marble 1. The chances of marble 2 turning out to be the color which you want may reduce. We'll solve some problems, then you will understand. Now, how to write conditional probability, this is important. Over here, now what is happening? B is dependent on A. That is, event B is dependent on event A. So whatever is in the denominator, no, this is in the numerator. B is dependent on A. So whatever is here has already occurred always. Huh? It has already occurred first, and B is dependent on A, always to be read like that. And the formula for that to calculate is B is dependent on A is B of A intersection B upon P of N it is, just put N here. Number of, this is the formula, N of A intersection B upon N of A. And suppose ulta, if you want to know how to read in the questions, probability of B given A will be already given. Probability of B given A. Now, as of now, you just write. First, did we solve one problem? It will be little difficult to understand. This is one part. This is probability of B given A. Now, the second one, second case. Probability of A, or I can say when A is dependent on B. Means what? B already occurred first. This is ulta. Suppose B has occurred, and now you want to calculate the first one. So probability A is dependent on B because B already occurred first. Formula will be N of same thing. Only thing here N of B will come. Now basically you have to find probability of A given B. B will be given and then you have to find out probability of A. Whatever is given will always go to the denominator. Whatever occurs first is always here. So we'll solve the first problem. I've sent these questions in the group. I just share the slide. Either you can take a print of those if you don't have the notes. I can write the questions later. First question. A ticket is drawn from a set of 20 tickets numbered from 1 to 20. And they're kept aside. Okay, one ticket is drawn.
Excuse me, teacher.
Yes.
Teacher, it's multiplication theorem.
Wait. One second. This is a die one I have to share. No, wait. And I shared the wrong page. But that also will come next. It is similar to this only. Just trying to think, locate where is the page. All look similar on here. Okay, here. First question is a die is thrown. If it is known that a number is greater than 3 has occurred, what is the probability that it is a even number? A die is thrown. Okay, it is known. Known means, remember that, given. Known is same as given. It is given that a number is greater than 3 has occurred. What is the probability? So event A is what? Either you can take it as event A or you can take it as event B. Event A is what? 3 has occurred. Event B will be what? It should be an even number. So you have to calculate event B based on event A. Now, what is in general? A die is thrown. The sample space for die will be 1, 2, 3, 4, 5, 6. These are all the possibilities. Now, event A is what is given, that it is what? A greater number greater than 3 has occurred on that. So A will be, what are the chances? Greater than 3 means 4, 5, 6. What is the probability that even number has occurred? So what are these even numbers? 2, 4, and 6. So these are the possibilities of getting an even number. Now what is asked? Probability of B. Now B is definitely dependent on A, so it has to be greater than 3 also. Probability of B now dependent on A, because this is given. As per the formula, number of n of A intersection B upon n of, as per the formula. Now just calculate how many, n means number of elements. So we need this. So just find out what is A intersection B. What are the common elements? 4 and 6 are the common elements. The number of elements in A intersection B is 2. Now just substitute here. Number of elements in A are how many? 3 are. The probability any doubts can ask. Intersection means always common elements between A and B. So isn't it correct? What has been asked? Which are the numbers? See, you know that it is greater than 3 and it has to be even number. Which are the two even numbers greater than 3? These are the only options. 4 and 6. So this will be basically, the chances are 2 of them. 4 and 6 which are greater than. Question number 2. Ten cards are numbered from 1 to 10 are placed in a box. Now a card is drawn at random from this box. If it is known that the number on that is more than 4, what is the probability that the number on the card is odd? Okay, first condition is what? There are 10 cards in the box, so sample space will be 1 till 10. Now a card is drawn at random from this box. So what is known given is A. You can consider given that So more than 4. So what all are the numbers? 5, 6, 7, 8, 9, 10 will be your events for A. Now what is B asking? B is number on the card is odd. So in general, which all will be the odd numbers you have to write? So sample spaces, there are 10 tickets. Given event A is what? Greater than 4 is there on the ticket. A will be 5, 6, 7, 8, 9, 10. B is what? Odd number appears. Which all are the odd numbers? You can take from here also, you can take from here also, because even if you take from here, finally intersection when you take, it will be common. We can take this also, no problem. 3, all the odd numbers from here, from the sample space. 3, 5, 7, 9. Even if you don't write this, you start from here, out of these odd numbers also you can do, no problem. Now I know that it's a conditional probability. So first only I'm finding n of A intersection B and keeping. What is A intersection B? The common numbers. So even if you don't write 3, it's fine, because finally you have to write only the common numbers. So 5, 7, and 9. Number of elements in A intersection B is 1, 2, and 3. Number of elements in A is 2, 3, 4, 5, 6. To apply the formula, we have to find P of probability that it's an odd number given that the number is greater than 4. How do we read this? Probability that the number on the ticket is odd given that it's a number greater than 4. So n of A intersection B, whatever is here in the denominator will be here. Substitute, answer will be 1 by 2. Third one, a family has 2 children. Find what is the probability that the both children are boys given that at least one of them is a boy. Given that now is at least one of them is a boy. And B is what? What is the probability that both the children are boys? The family has 2 children. So make a sample space first out of 2 children. So boy, boy, it could be girl, girl, boy, girl, or girl. We have 2 children. The sample space will be boy, 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 girl, and a boy. So the first one is a boy, second one is a girl. So these are the possibilities of the 2 children. Now given is what? Given will take it as A. At least one of them is a boy. Now look in the sample space and check where at least means minimum one should be a boy. There is one boy here, there is one boy here, this you cannot take. So A is what? These are the possibilities. Find the probability. B is what? Probability both are boys. Check here which is the option where both are boys. Only one option is there. So this is taken as one element, one possibility. So we'll find intersection. Intersection we will need while solving the problem. The only common is B, and the number of elements in here is 1. Number of elements in A is 3. These are the number of elements in A. So we have to find the probability. This is given. Sorry, B upon A. Given always goes here. So if you had taken B as given, no, then B would come. Whichever letter you use, no problem, but make sure given always goes to the denominator. So n of A intersection B upon n of A. How many elements are there? Just one common element. N of A is 3. The answer is 1 by 3. Next, fourth question that I'll write. It's small enough. The data I'll write. Fourth question, it is given. A is 6 upon 11, 5 upon 11. This actually should have been done after multiplication theorem. No problem. See, this is a formula, no? P of, I've given you this. Later I will prove it. Okay. These problems actually should be done after this. But everything is in terms of P, no? Okay, I'll do the multiplication theorem first. And then I'll solve from question number 4. Before doing the fourth question, I'll just do the multiplication theorem. It's very simple. Sometimes they ask in the exams to state the multiplication theorem and prove it. You have to state it also. This is the statement. If A and B are two events associated with sample space S, then these are both the proofs you have to prove. A intersection B is nothing but P of A into P of B by A. Or if you are using P of B here, it will be ulta. This is a statement, so we'll start with the proof. The first one, we just have to start like this. From conditional theorem, we have to remember the conditional formula. Theorem of probability. What are we trying to prove? We are using this. So start with this formula. What is P of B upon A? We have studied just now. I've given you conditional theorem of probability. What is P of B upon A? What is the formula given? Tell quickly. To solve what is B upon A, what is the formula? Just now, which formula I gave you all? What is P of B upon A?
So n of A intersection B upon n of A.
Yes, N of A intersection B upon N of A. So just write that formula as it is. Now we have to convert it in terms of probability. Any N, you know that. What is P of A? Nothing but N of A upon N of S. What would be P of B? Same way, N of B upon N of S. The moment I divide any N by sample space, it automatically converts into probability. Any event divided by sample space will give me probability. So what I have to do is just one extra step and then you prove it. Divide numerator this by N of S. Just divide both the things by sample space. So P of B by A will be equals to N of A of intersection B upon N of S. So this gets automatically converted into P, and this is also P. So P of B upon A is equals to P of A intersection B. It's the same formula. So whether I write N, next time remember, whether I write N or whether I write P, the formula will not change. Okay, calculation. Whenever I need N, I will use N. Whenever it is given in terms of P, I can use P also. No one will cut mark. You can use N also, you can use P also for the same formula. Because N of S is anyways gets divided. Now just take this other side. So it will get multiplied. That's the same thing. So just because you are multiplying here, it is called multiplication theorem. You are multiplying this here up. So this is the first proof. So if you just remember this formula, this is the step and just cross multiply. Same way second proof. Same thing from conditional list of probability. We know that now which one? The other one, A upon B. Divide numerator and denominator by N of S. So the moment you divide it with the sample space, it automatically gets converted into probability. Now just cross multiply and you'll get the answer. So take this, it will become multiplication. So it's the same thing, both the sides. For both the proofs, it is a intersection B only. Now what is the difference? Suppose if I am using P of B here, that goes to the denominator. So these are the same formula. The other one also is what P of A intersection B only. This is a proof, okay? We are finished with this. I'm just trying to compare. So if I'm using P dot A here as per the requirement of my problem, okay? Whenever based on the problem, which formula I have to use, either this or this. So if I need P of A is given to me, I can use this. If P of B is given to me, I need to use this. So P of A I know, then I cannot write A upon B here. I have to reverse it. Here it is there, whatever. The same thing I have to write the ulta. This goes here. Here see, same thing. This part is the same. So based on which letter you start with, this will change. So this is multiplication theorem of probability. Just writing it in terms of P and multiplying it on the other side. If this proof is asked, you have to write this much. State and then prove it. Now question number 4. If A is 6 upon 11, P of B is 5 upon 11, P of A union B is 7 upon 11, find first one is P of A intersection B, second one is P of A upon third is P of B by. First thing I have to find intersection. This is P of A. Until and unless specified independent events, don't use directly. If you use like this, like how we had used for independent, it will be wrong. This is used only if mentioned they are independent events. Otherwise, you know which is the formula. P of A intersection B is P of A plus P of B. This one you have to use. Now substitute. This is 5 by 11 is P of A intersection B. Now next, what has been asked is A upon. So directly instead of N now, nothing is given in terms of N. So I told you whether I write N of B or I can simply convert it into P also. Instead of N, I can use P also based on the problem. Here, P is a given. If N was given, I have to use N, no issues. Just substitute. What is P of A intersection B? 5 upon 11. What is P of B given? 5 upon 11. The answer is 1. Yeah, wait 1 second. This is 4, by mistake. This is 4. 11, 11 will cancel. 4 by 5 will be the answer. This is 11 minus 7, no? I did 12 by. So this is 4 upon 11. Just substitute it here. B is given as 5 upon 11. 11 is cancelling. Same way now calculate the other one. B upon A. P of A is given as 6 upon 11. 2 by 3 will be the answer. Fifth question. P of A is 2 by 3. P of B dash is 3 by 4. A by B is 4 by 5. Find P of A intersection B. Now, if you notice, P of A upon B is given. But in case you want to find A upon B is what? So this will be P of B. I need P of B. Okay? But P of B dash is given. Calculate what is P of B is always 1 minus P of B dash. Because they always, this plus this is always equals to 1. So it will be always the other part. 1 by 4. So what is P of A intersection B? That multiplication theorem we can use. You can put it here. I cannot use this one because it's useless. If I use this here, then this will become what a B upon A. But B upon A is not given in the question. So I cannot use this formula here. If I use P of A, then this will become B upon A. If B upon A was given, straight away I could use this. But now A upon B is given. So I have to use this formula only. So what is P of A upon B given? 4 upon 5. Or before that, you can just multiply here. So this is asked to calculate, which is here. So P of B is here 1 by 4. This is 4 by 5. Answer is 1 by 5. Question number 6. Let I'll share the slide. Question number 6 is there are two coins, okay, which are tossed at once. Tail appears on one coin and F shows one coin shows head. The number of, again, there are two events given. So we have to find E upon F for both the problems. Okay. So there are two coins tossed. Two coin tossed or one coin tossed two times. It means the same. The sample space will remain the same. Whether if two coins you are tossing side by side is same as one coin you are tossing two times. Okay, so whether they give this or this, the sample space will always remain same. Sample space will be either it can be head and head. It's like coin number 1 and coin number 2. The first time when you're putting, that is considered as coin 1. The second time when you're tossing, it's considered as coin 2. So that's the same logic applied. So whichever is given, same sample space, head, tail, these are the options. So first time what is given is, first problem, E is supposed to be tail appears on one coin. So find the event E, check out which option there is one coin of this tail there on one of the coin. It doesn't say coin number 1, huh? Any one of the coin. Any one of the coins among these two, there should be a tail. So this is there, this is there. This is also there. How many tails doesn't matter. Tails should appear. Tail appears only on one coin, correct. Not on both the coins. So here tail is appearing on one coin, here also. Here tail is appearing on two coins. We cannot take this. So head, tail, tail. So this is for event E. Now F is given as one coin shows head. One of the coins shows head. This is given in the question. No? This I'm not writing something on my own. As per the question, I just copied as it is. So now this part we have to frame. One of the coins showed head. So same thing. Now what you have to find? Find E upon F has been told. So what is probability of E upon F? Apply the formula. So same thing, instead of A and B, it is E and F. E intersection F upon E of F. Whatever is denominator here, it will be this. Or now, suppose if you are using sample space, instead of probability, I can use N now. Because I have to finally consider the number of elements here. Because here directly 1 upon 2 numbers are not given. 3 upon 4, we have to calculate. So whenever you use like this set form, we'll use N, number of elements. So first point, what is N of intersection? E intersection F is how much? What are the elements common? All of them. Both are common. So this number of elements in E intersection F is 2 of them. And how many elements are there in F? N of F we'll write here only. Number of elements in F are 2 of them. So substitute here. So answer is 1. Probability maximum can be 1. If you were getting more than 1, then it would be wrong. Then the second question. In the second question, E says no sample space remains the same. Head, 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 tail, tail, head, tail, tail. No tail appears. There should not be any tail in there. Only possibility where there is no tail. F says no head appears. That is tail. We'll have to find E intersection F because we will need in the problem. So it is empty. There is nothing common. So the number of elements in this is 0. And n of F is how much? 1. So we are asked to find P of E upon F. 0 upon 1 is 0. So like this, there can be many problems framed, okay, using head and tail. We have to just know how to form E, F, then you have to take the intersection and apply the formula based on what has been asked. Consider question number 7. In 7, E is given as 1, 3, 5. F is given as 2, 3. G is given as 2, 3, 4 and 5. First thing you have to find E upon F. So we know that probability of E upon F is, when pure numbers are not given, I told you use the formula N. So what all data we need? E intersection F. Find E intersection F. Which are the common elements? Nothing is common, no? Wait, I'll just check whether all the data is given. 3 is common here. E, between E and F, 3 is common. The number of elements in this is, how many elements? Just one element is. Then what else we need? Number of elements in F, how many are there? 2 of them. Just substitute here. This formula. Second one, P of F upon G has been asked. So F intersection G we'll have to find first. So find what are the common elements between F and G. 2 and 3 is common. The number of elements in F and G is 2 of them. And number of elements in G, 4 of them. Substitute here. Next one. Third one asked is P of E union F by G. So as per this is like A and this is like a B. Probability of A upon B is given as what? A intersection B. Instead of A, this is the whole thing. So it will be N of E union F intersection G. So it's like A intersection B. A intersection B upon N of B. So we have to calculate this part now. Union means you have to just combine all the elements. First we'll just find what is U union F. So E has these elements, F has these elements. So basically you just have to combine all the elements. Repeating elements you don't have to write. So combine all of them. So if you write like this, 2 times there's no point writing, just 1 time you have to write. Any repeating element, you just have to write it once only. So this is union. Now I want to see what is common with G. G is given as 2, 3, 4 and 5. So between this and this, which elements are common? So 3 is common, 2, 3 and 5 is common. So how many elements are there in this? 3 elements. N of G has 4 elements. This how much? 3. And these are 4. So 3 upon 4 will be the answer. Any doubts in conditional probability you can ask. Whatever I've covered so far, anything you've not understood. One more is the 8th one. P of B dash is given. Then P of A upon B is asked. Okay, so just apply the formula. P of A upon B will be P of A intersection B upon P of B. So you know what is P of B, you calculate. I'll put it here now. Now again coming back to multiplication theorem problem, we'll just continue with them. Now I had forgotten to give, soon after the multiplication there's a note given. Okay, what does multiplication theorem says? I'll just write it again. Multiplication theorem, what it says, P of A intersection B in both cases. If I'm using P of A here, it means I have to make it ulta. If I'm using B here, B will go here to the denominator. This is the multiplication theorem. Very simple to remember. B is here and B will go to the denominator. B and B will never come side by side. Now there's a note, what it says, for independent events, independent, A is obviously not dependent on B. Here, whenever this is not dependent on B, it doesn't make any difference. It will be straight away equals to B. And same way, A upon B, A is not dependent on B. Independent means condition is gone, doesn't work. That will be equals to P of A. So this is question number 1. Under multiplication theorem I've given. A ticket is drawn from a set of 20 tickets numbered from 1 to 20 and kept aside. Then another ticket is drawn. Find a probability that the ticket shows an even number. Now it depends what was your first one, because the count will change. If your first one was even number, then it will be one less when you pick up from the second time. So basically there are 20 tickets. So you remove one and keep aside. Now you have to see what happens on the second one. Okay, not second one. Directly they're asking what are the chances that it was a even number. Yeah. 2 tickets are drawn. Here it's mentioned. Okay, fine. So there's a box which it says there are 20 tickets. The sample space will be about 1, 2, 3 up till 20. And number of elements will be 20 of them. Let A be the event. Basically what they are trying to tell is if this is a even number, we have to check. First ticket, suppose this is the second ticket. What are the chances that the second one is also even? Why? Look, it's a little bit tricky question. Tickets show even number. The final line you read of the question, it says, what is the probability that the ticket shows an even number? The tickets means what? Both. Both the tickets should show even number. So ticket 1 also should be even, ticket 2 should also be even. They have not specified first one should be even, second one should be even. The one ticket is removed, kept aside, and second one is removed. What is the probability that the tickets show even number? Means both of them should have even number. So first we'll calculate the chances of the first one to be even. First ticket drawn is even. So what will be the event? 2, 4, 6, 8, 12, 14, 16, 18, and 20. So these are the chances when you take out the first ticket. Out of 20 tickets, which are numbered from 1 to 20, if you go to pick up the first ticket, okay, this all possibilities you can get. You can either get a ticket with number this, or this. So how many options are there? Number of might be 10. So straight away, what is probability? P of A is how much? N of A upon N of A. So 10 upon 20. That is 1 by 2. So probability that the first ticket showing even number is half chance. Now let B be the this. Second ticket is also even. Now obviously when you are drawing the second ticket, whenever you are drawing the second ticket is definitely based on the first, whether that was even or not. So probability is B is dependent on A. Probability that second ticket is even, given that this always I told you is read to be as given. Probability that second ticket is even, given that what is A, first ticket is also even. Then only both will become even, no? Only when the first one drawn was even, the second one you draw, then only this condition is satisfied that both tickets will become even. How many options you'll have? Consider one ticket drawn, first one is gone. How many options will be there? Just try to think. The first ticket which you drew from the box, even number came. Now you are keeping it aside. So how many options will be there in the box for you to pick up as a even number? How many even numbers will be left in the box? One even number is gone. Maybe we don't know whether what you picked up was 2, 4, 8, whatever. Now we are considering whatever you picked up was even number. So how many even numbers will be there in the box out of 10? Wherein how many even numbers will be there? Wherein you're there? Okay. Out of 10, first ticket, which is, these were the 10 options. Out of that, one ticket is gone out. And that we are considering it was a even number. One even is gone out. So when you're going to pick the second one, how many even options will be there in the box? How many of them will be there? Out of 10, one is gone out. Yeah, 9 will be there. So simple things, if you are not able to understand, you know what to be done. You draw, otherwise draw and see 10 tickets, all of them. Those are not this. Then one is gone. So 9 will remain. So this will be 9 out of the sample space. So 9 even. Now whole out of 20, one ticket is gone. So it will be 90. Why? Out of 20, one ticket is kept aside. So second time when you're picking up, you'll have only 19 options total, and out of that is a 9 even numbers, because one even number is already gone out. So now what has been asked, probability that both A and B are even. A and B means probability of A intersection B has been asked. So as per the multiplication theorem, P of A we know, so we use P of A formula. So we are using, automatically this will be B upon. So whenever they ask both, you have to use A and B formula. So substitute now. Both A and B are even is half into 9 out of. This will be the answer. Second question. And P of B is given as 0.8. We know that P of A upon B is what? P of A intersection B upon P of B. This is what we have to find. Now P of B we know 0.8, but we don't know P of A intersection B is not given to us. This also we don't know, this also we don't know. So we have to calculate this first. What we know is this formula. If I know this, this also is known. So what I'll do, first use this one and try to calculate this value. So P of B upon A is what? Same thing, P of A intersection B This is always common for both of this upon P of. Now this value I know is 0.4. P of A I know is 0.2. Just multiply it here. So from here I will get what is the value of P of A intersection B. This is 0.08. And now this value you put it here. One decimal you can shift both the places. This if you are moving one place, this also will move one place. 0.1 will be down. Third one, A and B given as independent. P of B is given as 0.4. P of A intersection B is given as, okay, this has been asked. P of A is given as 0.3. So I calculate for independent events. P of A intersection B straight away, P of A into P of B. For independent events straight away, this is multiplication. So 0.4, then get it as 0.12. First part is done. Second also for independent events, I told you, this doesn't matter at all. Straight away it will be P of A only. Which is, you can use that formula also in check. Or directly also if you use this way, what you will get P A upon B is what? P of A intersection B upon P of, same answer. What is the intersection B? 0.12. What is P of B? 0.4. Both the ways you will get same answer. For independent events, it does not depend on the denominator. Fourth one, is a proof. Prove that P of X union Y, this has been appeared in the paper many times. They only change the letters. Huh? Sometimes this can be A, B, C, any letters they use. So instead of X and Y and Z, it could be A, B, and C also. You can try later when you're practicing with these letters. Let's start with this one. Apply what is P of A upon B formula. What is A upon B? So this is like P of A upon B formula. So P of A upon B is P of N of A intersection this intersection this X union Y. This is the conditional probability theorem. A upon B is what? N of A intersection B upon N of B. Now distribute this. This Z belongs to this one also. This Z belongs to this one. Open up the bracket. This intersection X intersection Z, middle one is union. So Y intersection Z. I just distributed the Z to both the terms. To X also, to Y also. Now I'll use this as A and this as B. This whole thing I'll use it as A. Whole thing I'll use it as B. What is N of A union B formula? N of A plus N of B. We'll use this formula over here. So what will I get? A union B is what? N of A union B is N of A plus N of B minus N of A intersection B. Apply N of A union B formula. N of A plus N of B minus N of A intersection B. So this whole one thing I'm assuming it to be A. Now distribute that N of Z to all the three terms. Denominator, I'm just distributing it to everyone. In both the places, Z is common, so I'll just take out Z common. Z I'm taking common. Intersection Z. So because when you apply to both the places, you will get back the same thing. Now if you see, just apply this formula, it's nothing but what is A intersection B upon B? This is formula of conditional probability only. It's like A intersection B upon B. N of A intersection B upon N of B is nothing but x upon z. Just apply this formula back and see, you'll get back the same answer. Same way, n of y intersection z upon n of z is what? Y is dependent on z. You just have to look back in the question and just write a intersection b upon n of b is that is p. Which is nothing but equals to right hand. Till here, if you get, you just copy paste the question back. You can just refer your question, the main proof, automatically you'll understand this should be the answer. Just apply it back and see what is a upon b, a intersection b upon b. So that is correct. Okay, that's second question. I'll do it in the next class. And that question number 5. So we have to take another class for 11th standard now. I'll stop here.